I said we will not talk about eigenvalues until we have discussed the eigenvalue question. We are going to start the eigenvalue question today. We will not end it today. I think what is important is for me to get the ball rolling, give you the set of slides, and you go and spend time on it so that next week, I will go over some of these things again next week, but I just want to whet your appetite for it with it now. It is the eigenvalue question. The eigenvalue question is the big question facing tensor analysis. What are the eigenvalues and the eigenvectors of a tensor? What do these things mean? I want to show you the physical meaning of this. Let us just do a quick review. In our review, we are going to look at a lot of things about vectors and tensors. So in this, we are going to take issues. We're going to take 1, 2, 3, 4, 5, 6, 7, 8. We are going to review the relationship between vectors and tensors by looking at these 8 issues. And you can take this as a quick review of all you know about vectors and tensors. I'm just giving you a review of all you are supposed to have known or you already know now about vectors and tensors. This is just a quick look at it. Now, if you have a vector, there are 3 bases. In your secondary school and your first year, you are taught that those bases are I, J, and K. Or after some time, we said E1, E2, and E3. There are always 3. So it's EI, where I goes from 1 to 3. What about tensors? There are 9 dyad bases, 9 of them, and they are EI circle times EJ, where I and J goes from 1 to 3. So you have E1, 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 E2, E1, E3, all along until you get E3, E3. You have that. So that is the basis. For vectors, you have bases 3. For tensors, you have 9 bases. So both of them have bases. It's just that for vectors, there are 3. For tensors, there are 9. What about component form? When you want to express this in component form, for the vector, you have 3 components. So V1I plus V2J plus V3K, or V1E1 plus V2E2 plus V3E3. In tensors, you have the same. You have 9 bases and you have 9 components. So you have T11 E1 E1, T12 E1 E2, T13 E1 E3, T21 E2 E1, and so on. You just go on until you get 9 of them. Once you get 9 of them, you've finished the number of components that you are supposed to have there. Now, how do you evaluate the component? If I give you a vector V and I give you 1 base, let us say I give you the I base. How do you get the component in the I direction? You just take the dot product of the vector with I. So V dot I gives you the I component. V dot E1 gives you the first component. V dot E2 gives you the second component. V dot E3 gives you the third component. So no matter what you do, inner product of the vector and the base gives you the component in the direction of that base. Exactly the same happens to tensors. If you have a tensor, if I give you any dyad base, take the inner product with that dyad base, which again, it's the same thing as EI dot TEJ. It will give you each, for any choice of I and J, there will be 9 of these equations, and they will give you the 9 components. So once you know a tensor, and you are given the basis, you can form the components, just the exact, in as easy a way as you are able to do it with vectors. So when you are to evaluate components, the way you can evaluate vector components is exactly the same way you can evaluate tensor components. What about magnitude? Want to get the magnitude of a vector, you take the square root of V, of the inner product of the dot product of V and V with itself. Oh, the same thing happens to tensors. You want to get the magnitude of a tensor, take the inner product of the tensor with itself and take the square root of it, because the inner product of the tensor with itself is going to give you a scalar, and you can take the square root of that scalar. And what is scalar product? Scalar product is U dot V. In the tensor is S dot T. Go to the previous lecture, you'll see how these are defined. The second, there are two scalar products, but I did not define the second one, so forget about it. let us not worry about that one in this elementary introductory course. Let us talk about orthogonality. Orthogonality, the scalar product of two, if the scalar product of two vectors gives you 0, we say those two vectors are orthogonal. Similarly, two tensors are orthogonal if the inner product of the two tensors gives you 0. So orthogonality works exactly the same way it works for vectors as it works for tensors. What about 0 element? Oh, you have a 0 vector, which has 3 zeros. For the tensor, you have a 0 tensor, which is the annihilator tensor, which has 9 zeros. So it's the same thing. What about products? What products are defined for vectors? Oh, you have multiplication by scalar. You have scalar product. You have vector product, and you have tensor product. We deal, before you got to 300 level, you only knew about multiplication by scalar, scalar product, and vector product. The tensor product, which creates a tensor out of two vectors, we have just introduced that. Now, what kind of products do we now know with tensors? Of course, you can multiply a tensor by scalar. It works the same way. You can operate a vector on a, you can operate a tensor on a vector producing a vector. That can also be seen as a kind of product. You can do a composition of two tensors with each other. You can do a scalar product of two tensors with each other. There are other tensor products that are just beyond our scope here, but just know that they are there. But the ones that we are concerned about are here. So you can take this slide as a quick review of all that you have learned in vectors and tensors. If you remember this, you will see, and one thing this one does for you is that anytime you're having a problem with tensors, just remember that for anything that happens to a tensor, there is a vector equivalent. The only thing that differs here is that when you are talking of bases, they have 3, they have 9. When you are talking of component form, it's like this. When you are talking of evaluating a component, you take a scalar product. And here too, you take a scalar product. It's just that what scalar product means for tensors is different from what it means for vectors, but you also take a scalar product. You want to get the magnitude, you take the square root of the scalar product with itself. You want to get the scalar product, you just do the double dot here, and so on. So this is comparing vectors and tensors. Here we have established the relationship, and that relationship helps you because if you remember your vectors, you can always use that to remember your tensor. So that's the beauty of this. The eigenvalue question. Remember that if I give you a tensor, an arbitrary tensor, and I say, okay, how does it transform this vector? You have to work it out because you cannot know what the new vector will look like until you work it out. You cannot know its magnitude from the old one or its direction from the old one because both of them can change. If the magnitude does not change, you know that you are probably dealing with an orthogonal tensor. If the vector itself does not change, you know you are dealing with an hereditary tensor. If it gives you 0, you know you are dealing with an annihilator tensor, and so on. But generally, if I do not tell you more about the tensor I'm giving you, you can generally not predict what kind of vector it will produce, given an initial vector, until you work it out. The formulas, we received formula for computing principal invariance and took these formulas as definitions of principal invariance. This formula arises from deeper analysis. We already saw that the cofactor transform areas. We show that the determinant relates transform volume to the original volume. We will ask this question from the standpoint of tensors and show how it leads to several important results that greatly assist the engineer in solutions that may not have been possible otherwise. The eigenvalue question is introduced to you as a mathematical problem. It is an engineering problem, not a mathematical problem. The determinant and transformation of volumes. A parallelepiped formed by vectors u, v, and w is transformed to tu, tv, and tw by the tensor t. If u, v, and w are linearly independent, and that's the original volume is the scalar triple product. Therefore, that cannot vanish if the vectors are linearly independent. If t is invertible, neither can the transform volume, TUTV and TW vanish. So the original volume and the transform volume, neither of them can vanish. The ratio of the two volumes, that is the ratio of the new volume over the old volume, this fraction, why is it possible for us? I want the class to tell me, why is it possible for us to formulate this fraction? I want to tell me, why is it possible for us to formulate this fraction? Because it seems as if all the preambles were not necessary, but they are necessary. And I want you to tell me, why is it possible? There are two reasons why we can formulate this fraction. I want you to tell me any of them you know. Why can I formulate this fraction? Ogochukwu, what you have said is nonsensical. There's nothing called tensor triple product. There is a scalar triple product. There's a vector triple product. I've never had, until I'm speaking to Ogochukwu, I've never heard of something he called. James Udotong, because the denominator cannot be equal to 0. Why can't it be equal to 0? Why? Why is it not equal to 0? James. Why can't it be equal to 0? Because of linear independence. So we kept emphasizing linear independence because we want to ensure that the denominator cannot be 0. But before we can say it's not 0, it's first of all a scalar. You know that the scalar triple product gives you a scalar. You take the dot product of 2 and you take the cross product of 2 and then do a dot product with the third one. What you have at the end of the day. So in this fraction, what is on top is a scalar. What's at the bottom is a scalar, and both of them are not 0. We know that neither of them can be 0, provided U, V, and W are linearly independent. Because if we are going to choose 3 vectors, we will choose 3 vectors that are linearly independent. And once we choose these 3 vectors that are linearly independent, the bottom cannot be 0. But the top is not only not 0, it's also a scalar. And that is how you get the determinant of the tensor. If you want to make this easy, take this as I, J, and K. So if U is I and V is J and W is K, or E1, E2, and E3, what will be the value of the denominator? If Olajide Bitoye, I don't know what you are talking about. So what you are talking about, whatever you are talking about, you are wrong. Because it has nothing to do with what we are discussing here. The question I'm asking here is, if I want to looking at the fact that I can choose any 3 arbitrary linearly independent tensors, suppose I choose them to be I, J, and K, or E1, E2, and E3. What then would be the denominator? What would be the value of the denominator? If instead of U, V, W, I choose I, J, K. If instead of choosing U, V, W, I choose I, J, K, or E1, E2, E3, what would be the denominator of this expression? The denominator will be 1. So if you are looking for a way to calculate the determinant of your tensor, just choose I, J, and K. And so you know the first thing there, use the tensor on I, use the tensor on J, use the tensor on K, and form the scalar triple product. And the answer you get is the determinant of the tensor. So you can always, since when you want to find the determinant, you are allowed to choose any 3. You are allowed to choose any 3 vectors that are linearly independent. Your I, J, and K are linearly independent and they are simple. So why can't you choose them? Make life easy for yourself. So you can always get the determinant of a tensor in the easy way by using U, instead of using arbitrary U, V, and W, because the answer is independent of U, V, and W. You can choose any 3 vectors you like. The answer is always the same. That is the scalar invariant. And that scalar invariant is the ratio of the new volume to the old volume. So whereas a tensor transforms lengths, areas are transformed by the cofactor of the tensor, and volumes are transformed by the determinant of the tensor. So the cofactor and determinant have physical, geometric meanings. They are not just mathematical play. They have physical, geometric meanings that are useful in stress and strain analysis, and they are critical to the engineering understanding of analysis. So they are not just mathematics for mathematics' sake. So just note that. So the cofactor gives you an idea of the ratio of areas, and the determinant gives you an idea of the ratio of volumes. So we go back to the question. A tensor linearly transforms one vector to another. We cannot always predict the outcome of the tensor transformation, or other than the fact that we know it must be a vector and the transformation is linear. We know that if you transform a vector with a tensor, you get another vector. But we do not know much about what the vector will look like. If we know that transforming a tensor, the transforming tensor is a special tensor, such as the identity, spherical, annihilator, or rotation, we have additional information that can help us predict. So if you know that it's an identity, you know there will be no change. If you know that it's spherical, you know that its magnitude will change, but its direction will not change. If you know it's an annihilator, you know that everything will become zero. If it's a rotation, you know that its direction will change, but its magnitude will not change. There are some things, if you have a special tensor, you can. But suppose you do not, somebody gives you a tensor, he didn't tell you the tensor is identity, it's not spherical, it's not annihilator, it's not rotation, it's not projection, it's just an arbitrary tensor from somewhere. Let's see what. If you just get an arbitrary tensor from somewhere, the question we are posing is this. Suppose if we have a tensor and we do not know what, it's not a special tensor, but when you use it to transform a particular vector, it just elongates the vector. It doesn't do anything more than that. And this tensor is not spherical. You know, if it's a spherical, you say, no wonder it's a spherical. But this is a full-blown tensor. And all it does, it just elongates the vector. It does this not to all vectors, but to particular ones and for particular scalars. The transform vector is simply a scalar multiple of the input. If this happens, what's going on here? I give you a full tensor, and I give you a scalar, and I give you a vector. I say transform it. And when you transform it, all you get is the same vector I gave you, is the same vector as before, just only with a change of magnitude. And this particular tensor does not do it for all vectors. It just does it for some particular vectors. Then there is problem. We say, what is happening here? The transform vector is simply a scalar multiple of the input, and you know that this is not a scale, it is not a spherical tensor. Note what is happening here. The tensor is pretending to be a scalar, or at least a spherical tensor. So several questions arise. Why does it happen if it is neither a spherical tensor nor a scalar? Why is it doing like this? Is there any relationship between the tensors, the vector that it produces, that it produces on this special location? That scalar multiplier it comes out, is there anything important about it? What if that scalar multiplier is unity? These are the questions that arise. Let me go back, let me rewind. What are we facing here? I give you a tensor, and that tensor is not an identity. It's not a spherical. It's not a rotation. It's just an arbitrary tensor. And I give you a vector. I say, okay, can you give me the transformation? And when you give me the transformation, you get that the answer you get is just simply a linear multiple of the vector. And it happens. Maybe next week, I will bring some vectors and we'll work it together in class. You will just see this vector and this tensor. And you just see that when you do the transformation, all you get is a linear multiple. So, when that happens, the vectors that satisfy this equation we'll be looking at are called eigenvectors. Their corresponding scalars are called eigenvalues. Once you know the eigenvalues of a tensor, you already know the principal invariance in a form more simpler than the equations we saw last week. In fact, you know virtually everything you want to know about the tensor. I will want to close here. We are only 30 minutes into the new hour. I want you to go home with the poster. If it confuses you, don't worry. We will settle all that confusion. But I want it to lead you to reading more. Read about eigenvalues, eigenvectors. Read the notes before and after this. Read these slides when you get them to the full. And then by next week, I will go over the same thing again. But be sure you are prepared. Be sure you want to ask questions, because where we have reached now is the holy grail of tensor analysis. If all that we are doing before is to lead us to this place. And in fact, the most important thing about any tensor is eigenvalues and eigenvectors. And that is the center piece of everything an engineer wants to do with tensor analysis, to collect his eigenvalues and eigenvectors. These things have meanings. Let me see whether that's what I did in the next slide. Yes, eigenvalues and eigenvectors are often the quantities engineers seek in a typical tensor. Its physical interpretation is wide and diverse, depending on what type of engineer. If it's a material scientist or a civil engineer or a mechanical engineer, the eigenvalues represent the principal stresses, while eigenvectors represent the principal surfaces. If you are in dynamics, looking at vibrations, then the eigenvalues are the squares of the natural frequencies, and the eigenvectors are the mode shapes. If you're an electrical engineer, the eigenvectors and eigenvalues have to do with the oscillations of the circuit. So every engineering discipline deals with the eigenvalue problem, and they have fundamental meanings. They are not things that arose from mathematics. They are things that arose from engineering practice. And I'm going to spend more time on this next week, but I just want you to take this home, and I'm happy that we entered it a little bit. Today, we finished the discussion on cofactors. From there, we moved from that place to orthogonal tensors. From there, we moved to axial vectors and skew tensors. And now we are in the eigenvalue problem. We are going to continue the eigenvalue problem next week, but I'm going to go back to the beginning and discuss it again to be sure that I'm carrying everybody along. The eigenvalue problem is too critically important. We cannot rush over it. We must know it. It has to be properly understood. And the eigenvalue problem is the primary reason why engineers study tensor analysis. The eigenvalues and eigenvectors are critically important. So I will leave you at that, and you can now go on your break and come back next week. Thank you.